So, dear student, continuing to the chapter number 2, the second part. So, we were discussing about the confusion matrix, and in the confusion matrix, we saw that before that one, we need to divide the data into the training data and the testing data, and then we will see for accuracy and specificity and other formulas our confusion matrix. So, we need to divide into two parts: the training one and the testing, and after that one, dividing into these two parts. Yeah, so we have divided into two parts, and then the first part is like the training and then testing with the cross validation. So what we see here, after that one, we apply logistic regression, we apply support vector machine, and we apply KNN. And then what we got it. So a confusion matrix for each method we applied, and then see that where is more accuracy and where is more like error. So this is churn and not a churn, and then churn and not a churn, or you can say 0 and 1, 0 and 1, and then you will see how it works. So true positive, the green, and false positive. So what we see here, if you apply KNN algorithm, in that case, how many times samples were corrected classified, and how many times were not corrected classified, right? So these are the data: 182 times corrected classified, to the 26 times we have 31 times, and 150 times, right? So in that case, we see that how the things are going on, and so the total were 332 times. So if we add the green one, it is 332, and if we add the orange one, it's 57. Similarly, for the KNN, the answer is, so if you compare this with the previous one, there is, this one is not the desired one, because here is the corrected one is very less, so we don't choose this one. And this one is KNN is it is more preferable. So yeah, so here these another examples: Reboot, Moneyball, Forrest Gump, and favorite movie, right? So some people liked it and some people don't like it, right? So so in that one, so for example, we have different choices and the favorite movie. In this example, we have three items to choose, right? So what are the three different items? Here we have a Moneyball, I, Robot, and Total Recall, right? So these are the three different items, or three different movies, you can say. So in that case, so we need the confusion matrix becomes bigger a little bit, and all the green are correctly classified, while the other are not correctly classified. So in this example, we have four items to choose. Because why we need to choose the four items? Because four movies are there, right? So we need to choose the best movie, or people liked it more. So in that one, the confusion matrix would be more bigger. Yeah. So what about the sensitivity and specificity? So this is a very good example with the graphical one. You can say, so all healthy true negatives, and then six with the true positive and false negative, and cutoff values. You can say the tails value. These are called cutoff values. And we can also, sensitivity is how it works, how it looks in graphically, and also you can see the specificity on the down in the corner side, down right corner side, and NPV on the upper side, and PPV on the left hand side. So these are the total things we have it. So in summary, confusion matrix tells you what is the machine learning algorithm did right and what it did wrong, right? So this is a very good tool to evaluate your model. So it tells you about the percentage of customer churns were correctly identified, and sensitivity means the TP, which is true positive, divided by the true positive plus false negative. So this is very simple formula, and you can easily put the values and find out the sensitivity. And similarly, for specificity is a bit different. So you need to pick the true negatives, divide by the true negatives plus false positive, and you will get your solution. So what is specificity? Tells you what percentage of customers don't churn were correctly identified. So sensitivity means what percentage of customer churn were correctly identified, and this were don't churn were correctly. So this is the negative opposite of that one. So here is like more some details about that one. This is one of the example, and you can find practically that how it happens. So you need to the true positive is 139 divided by the true positive, and the 32. 32 is on the left hand side, and you will get the sensitivity. Sensitivity is here 0.81, and specificity is different, and it is about the other side, which is 112. So see on the diagonal, in the previous one, we selected the upper diagonal, and this one in the lower value in the diagonal. And now let's calculate sensitivity for this one. And sensitivity is for the decision tree, okay, and which is we call it random forest. So many decision tree becomes random forest. And this is specificity, and this is very simple formula, and you just need to compute the values in it. So we would choose the logistic regression here model. Why? If correctly identifying the customer don't churn, more important than correctly identifying the customer leaving, right? So sometime if the customer leaving, so that is called like churn, and correctly identifying for example don't churn. So sometime for us don't churns are more important rather than the churn. So sensitivity tells us the random forest is slightly better at the correctly identifying the positive churn in our case, and while specificity tells us logistic regression is slightly better at the correctness. So sometimes it depends on that one on the values after calculations, and it helps you out that which one is better for your data. Biasness and variance. So sometimes you do some are some algorithm are biased towards the data, and we need to see which is where is the biasness and where is the variance. So some have lower biasness, I can see, and low variance. So the first example is on the low bias and low variance, while other one is the biasness is low but the variance is high. There is a more distance in the points. In the third one, this corner, this one is one with a high biasness because it is not targeting the exact value, and the variance is also low. They are very interconnected. While the last one in the right down corner, here they are not hitting the exact point. So here there is high biasness, and the distance among the points are also very much so, we can say high variance. So biasness and variance you can see over here. Light cats tends to be a short, okay. So and heavy cats tends to be taller, right? So here we see where is the biasness, but after a certain weight, cats don't get any taller, just more obese, right? So here we compute the data according to the cats, okay, and then we find it out, and we will see that where is the biasness. So ideally, we would know the exact mathematical formula that describes the relationship between the weight and height, and then, but in this case, we don't know the formula, so we are going to use machine learning methods to approximate this relationship. And the first thing that we do is to split the data into two sets, one the training and other for the testing. The blue dots are for the training, and the orange are for the testing. Blue dots are they are training sets, and the orange are for testing. So the first machine learning algorithm that will we use is linear regressions, and also called least square as well. The linear regression fits a straight line to the training set. So the straight line doesn't have the flexibility to accurately replicate the arc in the true relationship. So the first machine learning algorithms are, so that is mostly in social sciences also the linear regression is used, and least squares are used, or in some of the software like equation models, or structural equation models. Yeah, smart PLS, they also they use least square. The linear regression fits a straight line to the training set, and the straight line doesn't have the flexibility to accurately replicate the arc in the true relation. So I mean, it doesn't touches every point. So no matter how we try to fit the line, it will never curve, so for that one we cannot trust the linear one. We go for the non-linear, that the straight line will never capture the true relationship between the weight and height. So no matter how we fit in the training set, because straight line cannot be curved like the true relationship, it has a relatively large amount of the bias, okay. So this is the bias which we are talking in the previous slides. Another machine learning method, might fit squiggly line to the straight. Yeah, this is squiggly line and like zigzag line, I can say, because squiggly line can handle the arc in the true relationship between the weight and height, and it can be very little bias over here. So we can compare how well the straight line and the squiggly line fits the training set for calculating their sums and square. So see over here the differences. Okay. Notice how squiggly fits the data so well that the distances between the line and the data are all zero, right? So here there is no error. So here the squiggly line wins. So in the context, whether which one is so in the training it wins, but let's see in the testing. So how about the testing set? The straight line wins or other wins? Let's see. So even though squiggly line did a great job fitting the training set, it did a terrible job fitting the testing set. So the machine learning, the difference in fit between data is called the variance, right? So if there is more variance, so it's not fitting into the into our model, right? So it means that like the straight line is seems to be winning in the testing. So the squiggly line has a low bias since it is flexible and can adapt to the curve in the relationship between the weight and height. But the squiggly line has high variability because it results in the vastly different sum of the squares for different data sets as well. So in this case, we can say that the straight line has more power. So it has low bias, squiggly line, but it is flexible and can adapt to the curve in the relationship between weight and height. And while the squeezy line has high variability because it results in the vastly different sum of the square and this one. So it will be hard to predict how well the squiggly line will perform with the future data sets. It might do well sometimes, and other times it might be terribly for us. So in contrast, straight line has a relatively high bias since it cannot capture all the correlation between the weight and height, but it has a low variance, right? So in this case, so what is the verdict? The verdict is that one straight line might only give good predictions and not the great prediction, but they will be consistently good prediction as well. Because the squiggly line fits the training set well, but not in the testing set. So here it fails, right? So we say that squiggly line is overfitting, it covers all the points, but in the testing it fails. In machine learning, the ideal algorithm has low bias and can accurately model the true relationship. And it has low variability by the producing the consistent prediction across the different data set. So we need to find a sweet spot between the simple model and the complex model. So this is so three commonly used methods for finding the sweet spots between simple and complicated model are regularization, boosting, and bagging. So these three are methods which is very much used in the machine learning. And then we have a second last topic, which is ROC and AUC. So ROC is the region of convergence we can see here, and it's AUC is between, you can see the different lines between which is drawn between the true positive rate and the specificity. So and we false positive rate, and it's from 0 to 100 and 0 to 100, and there is some cutoff way here and no discrimination here with the A 0.5. And so this is one of the example for ROC and AUC. So for example, for the obese and not obese example, so what are ROC and AUC? When we are doing logistic regression, y-axis is converted to probability that cat is obese, right? So we are here 1 and 0. And in this case, if someone told us that they have a heavy cat that weighs this much, so that is case, in that case, there is some point. Then the curve would tell us that there is a high probability that a cat is obese. So there is a point here. Now you can see over here, then curve would tell us that there is a low probability that cat is obese. So what do you think about this one? Here, where is the exact point and where is the ROC and AUC? So the logistic regression tells us the probability that a cat is obese based on the weight. So I hope you got the point. So see you in the third part.